The first city on Mars will be built by robots. This video is a tour of 25 specific autonomous machines that will construct our future off-world infrastructure, from lunar launch pads to Martian resource networks. The shift from human hands to robotic ones is not just a choice, but a necessity for speed, safety, and survival in the brutal environments of space. You will see how a silent army of specialized systems, from microscopic tunnelers to orbital factories, will work in concert to turn barren worlds into livable outposts. By the end, you will understand the complete blueprint for how robotic industry will physically build our interplanetary future. How will a machine that builds copies of itself change the rules of expansion? And what does a construction site look like when every worker is a drone? The vision is clear, but the path is built by machines we are only now learning to create. What does it mean for our future when the builders arrive long before the inhabitants? Before a single foundation can be poured, the land must be understood. The first boots on this ground are not worn by astronauts, but by the autonomous site Surveyor, a robotic rover built to see the world in a way we cannot. Picture a machine that moves with a slow, deliberate purpose. Its array of sensors constantly sweeping the alien landscape. It sees not just rocks and dust, but the very structure of the world beneath its wheels. With LIDAR, which is like a laser-based form of vision that builds precise three-dimensional maps, it charts every boulder, every slope, every potential obstacle. But its vision goes deeper. Using ground-penetrating radar, it peers below the surface, mapping the stability of the soil, locating hidden voids, and identifying subsurface ice deposits that could be vital resources or hidden dangers. Finally, its spectroscopic sensors analyze the chemical composition of the rocks and regolith, searching for the best raw materials for construction or signs of minerals that could complicate building. This machine is the ultimate scout. Its singular mission is to find the perfect patch of ground, the one site where a landing pad will be perfectly level and stable, or where a habitat module will have the strongest foundation. It does not simply take pictures, it builds an entire digital twin of the site, a hyper-detailed three-dimensional model that becomes the master blueprint for every machine that follows. This model is then broadcast to the entire robotic construction fleet, giving each excavator, each printer, each assembler the exact same perfect understanding of the terrain. The surveyor does not build, it teaches the land to the builders, translating a chaotic, unknown environment into a clear, actionable plan. This is how construction begins, not with a bang, but with a quiet, comprehensive scan, turning mystery into a mapped and measured reality. With a perfect site now mapped and understood, the silent ground begins to stir. The Regolith excavator and sorter is a machine of immense, quiet power, built not for Earth, but for the gentle pull of the Moon or Mars. In these low-gravity environments, a traditional bulldozer would simply float and skid, its weight useless. This machine is different. It might use wide, gripping treads or even innovative legs to anchor itself, applying force with a precise, deliberate intelligence. Its primary task is elemental: to dig and to move. It carves out landing pads, levels ground for habitats, and trenches channels for infrastructure, moving mountains of loose rock and dust, what scientists call regolith. But here is where it becomes more than just a cosmic shovel. Every scoop it takes is not merely waste, it is potential. As the bucket lifts, an integrated sorting system springs to life. Using a combination of sieves, magnets, and spectral analyzers, the machine performs a rapid, automated triage right at the worksite. It separates the precious from the mundane. It might isolate grains of ilmenite, a mineral rich in iron and oxygen, diverting that valuable payload to a separate hopper for future processing into breathable air or rocket fuel. At the same time, it identifies and sets aside the inert, bulky material, the perfect aggregate for making concrete or radiation shielding blocks. This transforms the entire logic of construction. There is no separate mining operation and no dedicated waste disposal. The act of digging the foundation simultaneously harvests the resources to build the walls and even create the air inside them. The excavator and sorter is the first true industrial cycle on a new world, a single machine that turns barren ground into both a building site and a supply depot. It works in constant dialogue with the surveyor's map, knowing exactly where to dig deepest for resources and where to use the sorted bulk for immediate fill. This is how you build a future from the very ground you stand on, with nothing going to waste. The sorted regolith now awaits its transformation, moving from raw material to solid structure. This is the moment for the mobile three-dimensional printing gantry, a robotic architect that builds not with bricks, but with controlled flows of dust and binder. Envision a massive skeletal frame, like a bridge on the move. It might roll on wide tracks or even stride on articulated legs, positioning itself with meticulous precision over the exact footprint dictated by the digital site model. At its heart is a sophisticated print head, a nozzle that does not extrude plastic but a carefully calibrated mixture. In one method, it sprays a liquid polymer binder onto a precisely laid bed of the local, sorted regolith, fusing the grains together instantly. In another, it might use a concentrated beam of sunlight or a microwave emitter to sinter or fuse the dust particles directly, melting them just enough to bond. Layer by painstaking layer, following the invisible blueprint in its memory, the gantry traces its path. It does not tire, it does not waver. What emerges from this slow, additive dance is not a prefabricated part, but the very bones of the outpost itself. It prints the thick, curved walls of a habitat, their shape optimized for strength and internal space. It prints the monolithic slabs of a radiation shield, building up meters of protective mass. It can even print the foundational piers for a landing pad or the channels for utility conduits, all as single, seamless structures. There are no seams, no weak joints where sections meet, because the entire component is one continuous piece, grown from the ground up. This machine turns the site itself into the factory, eliminating the need to transport bulky prefabricated walls across millions of miles of space. The gantry's work is a quiet revolution in scale, proving that the most imposing structures on a new world might be printed into existence, as if the land itself is learning to build shelters for those who will one day call it home. But a printed structure is only a shell, a silent monument without the vital systems that give it life. The true nervous system of an off-world colony will be laid not by hand, but by a living, shifting carpet of purpose. This is the domain of the swarm of microtunnelers, thousands of small, insect-like machines that work as a single, intelligent entity. Each individual unit is simple, perhaps no larger than your hand, equipped with a compact digging head and basic sensors. Their power lies not in their size, but in their overwhelming numbers and perfect coordination. Released onto the prepared site, they communicate constantly, a buzzing network of data that guides their collective behavior. Their mission is to carve the hidden arteries of the colony. They descend into the regolith not to build grand chambers, but to excavate a dense, intricate lattice of tiny utility tunnels. Picture the root system of a vast tree, branching and spreading just beneath the surface. One branch will carry shielded fiber optic cables for communication. Another will house life support piping for water and air, while a third is reserved for power transmission lines. This underground network is a strategic masterpiece. By burying these critical lines, the swarm protects them from the two great dangers of the surface: the relentless bombardment of cosmic and solar radiation that can degrade materials over time, and the extreme temperature swings between daylight and darkness that can stress and crack exposed components. The tunnels provide a stable, insulated environment, a constant thermal blanket that ensures the colony's heartbeat remains steady. The swarm works with a distributed intelligence. If one unit encounters an obstacle too hard for it alone, it signals for reinforcements, and others converge to help. If a tunnel segment is completed, the units simply move on to the next coordinate in the shared blueprint. There is no central foreman shouting orders, just a quiet, relentless progression of collective effort. This is how infrastructure is woven into the very fabric of the new world, not as an afterthought, but as the first, most vital layer of civilization, hidden from view but essential for every breath and every bit of data that will ever flow. Above the intricate web of tunnels, the skeleton of the colony begins to rise piece by piece. The autonomous welding and assembly drone is the artisan of this new skyline, a machine that builds in 3 dimensions with the grace of a bird and the precision of a master watchmaker. These units come in many forms. Some are agile, multi-rotor flyers that hover with a quiet hum, while others are crawling climbers that scale the growing structures with magnetic grips or micro-claws. Each is equipped with sophisticated manipulator arms, ending not in hands, but in specialized tools, most commonly a precise welding torch or a bonding applicator. Their raw materials are the large, prefabricated components shipped from Earth or manufactured in local robotic factories, the heavy trusses for vast solar arrays, the curved hull segments for pressurized greenhouses, the complex nodes that will form the hubs of a habitat cluster. The drone's mission is to take these giant puzzle pieces and fuse them into a single, airtight, load-bearing whole. It begins by scanning the alignment of 2 components with laser guidance, confirming a fit accurate to within a fraction of a millimeter. Then, with a steady, unwavering touch impossible for a human in a bulky suit, it applies a perfect, continuous weld along the seam. There is no tremor, no fatigue, just a smooth, glowing line of molten metal that cools into a bond as strong as the original material. This process repeats thousands of times, a symphony of precise connections. One team of drones might work in concert to lift and secure a long truss beam for a solar farm, while another group meticulously seals the hemispherical dome of a water recycling plant. They operate in a carefully choreographed ballet, avoiding collisions through constant communication, each aware of the other's position and task. Their work transforms a collection of parts into a functional anatomy, creating the strong bones and sealed skin that will protect life from the vacuum outside. They are the final step in giving physical form to the digital blueprint, the quiet force that turns delivered hope into permanent home. The final weld cools, sealing the colony's outer skin, but the true revolution in construction is only just beginning to stir within a different kind of machine. Deep inside a shielded workshop bay, the self-replicating fabricator represents a fundamental leap in logic, a system designed to turn scarcity into abundance through the most elegant of cycles. This is not merely a 3-dimensional printer, it is a machine that can, with careful guidance, build another machine. Its core function is to use the very materials harvested by the excavators and sorters, the metals and ceramics and polymers derived from the local regolith, to manufacture not just building parts, but the critical components of another fabricator. Picture a robotic arm assembling a duplicate of its own joint assembly, or a print head carefully crafting the logic board that will guide its twin. This is the key to exponential growth. Instead of waiting years for a new industrial robot to be built on Earth and launched at immense cost, a single fabricator could, over time, create a second. Those 2 could then create 4, and those 4 could become 8, rapidly scaling up the colony's entire manufacturing base from a single seed. The paradigm shift is staggering. It transforms the mission from one of shipping every single tool to one of shipping only the initial, irreplicable blueprint and the seed machine itself. Everything else, from simple wrenches to complex sensor arrays, could potentially be sourced locally. This capability would unlock a future where industrial capacity grows in harmony with the colony's needs, without the bottleneck of interstellar supply chains. Yet, such profound power necessitates equally profound safeguards. The concept is governed by layers of control protocols, often called closure laws, which are hard-coded into the machine's deepest operating systems. A fabricator might be programmed to replicate only 90% of itself, with the final, most complex 10% of components requiring specialized parts or verification codes from Earth. This ensures that every new generation remains under human oversight, a necessary check on exponential, uncontrolled replication. The goal is not to create an independent mechanical species, but to establish a tool of incredible efficiency, one that builds the future literally from the ground up, while remaining firmly a part of our designed and intended legacy. It is the ultimate expression of turning a new world into a home by teaching that world how to build the tools for its own transformation. High above the blue marble of Earth, a different kind of construction material drifts silently through the void. The orbital debris recycler is not a machine that builds, but one that first must clean, turning a problem into a profound opportunity. These autonomous spacecraft are the celestial custodians of our future, equipped not with traditional tools, but with specialized nets, grappling arms, and compact furnaces. Their mission is to hunt down the ghost fleet of our past, the defunct satellites, spent rocket stages, and countless fragments that clutter the valuable real estate of Earth and lunar orbit. With gentle, calculated maneuvers, a recycler closes in on a derelict communications satellite. Its robotic arms extend, latching onto the structure with a secure grip, a capture made infinitely complex by the extreme speeds of orbital mechanics. Once secured, the real work begins. The spacecraft is a flying factory. Using cutters and torches, it systematically dismantles its catch, separating valuable aluminum alloys, titanium, and other metals from the plastics and composites. This sorted scrap is then fed into a contained processing furnace, where intense heat, often focused solar energy, melts the metals down into pure, standardized ingots or wire feedstock. This transformation is a complete reversal of logic. A satellite that ended its life as hazardous clutter is reborn as the foundational stock for new construction, but construction that happens in space for space. The implications are immense. Every ton of metal harvested in orbit is a ton that does not need to be launched from Earth's deep gravity well at a cost of millions. It provides the raw material for building larger space stations, fuel depots, or shipyards right where they are needed, dramatically reducing the cost and increasing the scale of our off-world ambitions. Furthermore, each captured piece makes the orbital highways safer for future missions, slowly clearing the dangerous cloud of debris that threatens every working satellite and crewed vehicle. This machine represents a critical step toward a sustainable presence in space, where we learn to live not by constantly importing supplies, but by closing the loop where our past endeavors literally become the foundation for our future. While the orbital recycler harvests the sky, another machine seeks a treasure far more precious than metal, hidden in the eternal shadows. The Cryogenic Ice Miner is a specialist of the deep cold, engineered to venture where sunlight never reaches and temperatures plummet to hundreds of degrees below zero. Its target is water, but not in any form we know on Earth. Locked within the permanently shadowed craters at the lunar poles or buried beneath the rusty soil of Mars lies water ice, a crystalline resource more valuable than gold for a fledgling colony. This machine is built like a subterranean industrial complex on treads. It begins with a heavy, low-vibration drill, designed to core through frozen regolith without generating heat that could prematurely vaporize its prize. As it bores deeper, its sensors, likely a form of neutron or radar spectrometer, map the concentration of ice in real time, guiding it toward the richest veins. Upon reaching a deposit, the extraction process begins, a delicate operation in an environment where ice behaves like solid rock. One method might use a heated probe to gently melt a localized pocket, sucking the resulting slush into insulated containment vessels. Another could employ a mechanical auger to chip out chunks of the frozen mixture, which are then transported to an onboard processing plant. Here, in a series of sealed chambers, the real magic happens. The icy regolith is slowly warmed, and the water vapor is carefully captured. It then undergoes a multi-stage purification process, removing dust and any potential contaminants, resulting in bottles of pristine, liquid water. The significance of this single output cannot be overstated. This water is the lifeblood of the colony in the most literal sense, for drinking, for growing food, and for the chemical processes of life support. But its utility expands far beyond biology. Water is a superb shield against cosmic radiation, meaning these mined blocks of ice could be used to line habitat walls, protecting inhabitants. Most strategically, through the process of electrolysis, this water can be split into its core components, hydrogen and oxygen, the very same powerful propellants that fuel rockets. A single mining outpost could therefore become a cosmic gas station, refueling ships for the journey home or for voyages deeper into the solar system. The cryogenic miner does not just extract a resource, it unlocks the entire economic and biological potential of a world, turning silent, frozen shadows into the wellspring of a living, breathing, and traveling future. With water and metals secured, the colony's next need is a steady, beating heart of power. The photovoltaic array deployer is a specialist in capturing light, transforming the relentless solar wind into the electricity that will animate every machine and warm every habitat. This system is often a hybrid, combining the steady, grounded purpose of a rover with the graceful reach of aerial drones. The rover serves as the mobile base and anchor, transporting tightly packed rolls of ultra-thin, flexible solar film to the chosen site, a vast, sun-drenched plain carefully cleared by earlier machines. Upon arrival, the deployment begins not with human hands, but with a carefully orchestrated mechanical ballet. Robotic arms on the rover unfurl the sheets of photovoltaic material like a cosmic sail being set, laying them out across the prepared ground. Meanwhile, aerial drones lift into the thin atmosphere, each carrying a support strut or a connecting cable. They fly to precise coordinates, lowering their payloads into receiving clamps on the rover or on already placed panels, building a lightweight, durable framework that holds the solar fabric taut against the wind. But the deployer's job does not end once the array is physically laid out. Its intelligence is in constant operation, seeking perfection in energy capture. Each panel or each section of the film is mounted on a micro-actuator, a tiny motor that allows it to tilt and turn. Linked to a central sun tracking algorithm, the system constantly adjusts the angle of every surface throughout the long planetary day, ensuring the panels are always directly facing the sun, squeezing the maximum possible wattage from every ray of light. This is a critical advantage in places like Mars, where the sunlight is already much fainter than on Earth. Then comes the maintenance, a silent battle against the ever-present dust. These environments are choked with fine, electrostatic regolith that settles on every surface, steadily blotting out the sun and crippling efficiency. The deployer is equipped to fight back autonomously. Some systems use gentle, periodic vibrations to shake dust loose. Others might employ a subtle electrostatic charge that repels particles, or even deploy soft, rolling brushes across the panel surfaces at scheduled intervals. This self-cleaning capability means the power plant maintains its output for months or years without a single astronaut needing to step outside for dangerous, tedious manual work. The result is a living, responsive skin of energy that grows with the colony, its silent, daily adjustments and cleanings ensuring that the lifeblood of electricity never falters, powering the lights, the heaters, the oxygen generators, and the next generation of machines ready to build even more. Power flows, but the colony cannot be a collection of isolated islands. Connectivity demands pathways, and these are forged by the autonomous road paver, a machine that turns chaotic dust into a ribbon of order. This is not a simple asphalt truck, but a mobile factory designed for alien geology. It begins by ingesting the very regolith beneath its treads, feeding it through an internal processing drum. Here, the raw, loose soil undergoes a transformation. One method uses focused solar energy or microwave beams to sinter the material, heating the dust grains just enough for them to fuse together into a solid, ceramic-like surface. Another approach might mix the regolith with a small, imported chemical binder, a stabilizing agent that reacts with the soil to create a tough, concrete-like pavement. As it processes, the paver moves forward with a slow, deliberate pace. Behind it, a series of rollers and finishing blades smooth the newly formed surface into a perfectly flat, hardened roadway. The result is a permanent artery, a stark, gray line etched across the rust-colored landscape. These roads are not a luxury, they are a critical safety and efficiency multiplier. For the colony's rovers and transport vehicles, a prepared surface means dramatically reduced wear on wheels and motors, and far less risk of becoming boged down in treacherous, loose soil. It enables faster, predictable travel between the habitat, the mining outpost, the solar farm, and the landing zone, turning a sprawling work site into an integrated community. The paver works from the central digital blueprint, laying these routes along the most logical and stable corridors identified by the original surveyor. Each road it creates is more than just a convenience. It is a statement of permanence, a physical commitment that the outpost is not a temporary camp, but a growing, connected settlement where every journey has a solid foundation. The roads connect the industrial sites, but a colony's true sustainability will be measured in green, not gray. The robotic greenhouse assembler is tasked with building the very first living ecosystems on a dead world, creating spaces where life can take root long before the first farmer arrives. These machines are specialists in controlled environment agriculture, and their work begins with the structure itself. Some deploy and seal vast geodesic domes made of transparent, radiation-resistant polymers, capturing every possible photon of sunlight. Others, for greater protection, might bore into the side of a cliff or lava tube, assembling modular, insulated chambers deep within the rock, where artificial light will be the sole source of energy. Inside these sterile shells, the assemblers become gardeners of the inorganic. With precise robotic arms, they install the intricate skeletons of hydroponic and aeroponic systems, laying out networks of pipes, channels, and misting nozzles where soil will never be needed. They position racks of growing trays and install banks of full-spectrum LED lights, each tuned to specific wavelengths that optimize plant growth for nutrition and yield. The climate is then meticulously crafted, sealing the environment and introducing a carefully balanced atmosphere rich in carbon dioxide, with temperature and humidity controls set to an exact ideal. Finally comes the most hopeful act of the entire construction process, the seeding. From sterile, pre-loaded cartridges, the machines deposit seeds into their assigned growing mediums, a first planting performed by cold, logical machines for a harvest they will never consume. But their role does not end with assembly. These robotic stewards remain on duty, their sensors constantly monitoring moisture levels, nutrient concentrations in the water, and the delicate health of the sprouting plants. They adjust lighting schedules, administer precise doses of fertilizers, and even employed gentle robotic pollinators or targeted misters to mimic rain. Their goal is to establish a fully functional, producing biosphere that is already yielding fresh greens, vegetables, and perhaps even dwarf fruit trees by the time the human crew steps through the airlock. This machine does not just build a facility, it births and nurtures a biome, transforming a sealed chamber of machinery into a living larder and a psychological sanctuary, ensuring that the first human breath inside is scented not with sterile metal, but with the profound, forgotten fragrance of growing things. A silent, thriving colony is still an island without a voice. The communication tower Erector is the machine that weaves isolated efforts into a single, thinking network. This autonomous system specializes in creating the high ground of information, deploying tall, spindly towers that rise like metallic saplings from the dusty plains. Its design is a marvel of efficient transport, with towers packed flat in compact, reel-like containers on a rugged Rover chassis. Upon reaching a Surveyor-designated site, often a strategic high point for maximum coverage, the deployment sequence begins. A robotic arm lifts the tip of the packed tower, and through a combination of unfolding segments and a controlled winching system, the structure rises skyward, locking into place as it extends. These are not heavy steel constructs, but ultralight lattices made from advanced composites, engineered to withstand alien winds without the need for deep, labor-intensive foundations. Each tower becomes a nerve center, bristling with multi-band transceivers, laser communication terminals, and local network routers. Their primary function is to create a resilient mesh network, a web of signals that blankets the entire operational zone. Every autonomous machine, from the deepest tunneling microbot to the highest flying assembly drone, connects to this network, constantly streaming its status, location, and sensor data. This live feed creates a shared consciousness for the robotic workforce, allowing an excavator to warn a nearby transport rover of a ground shift, or a solar array deployer to request a cleaning drone because its power output is dipping due to dust accumulation. For human inhabitants, this network is the lifeline of civilization, enabling high-bandwidth communication for science data, video links with Earth, and the seamless operation of life support monitoring systems. The towers ensure that no machine works in ignorance and no colonist is ever truly alone, stitching the physical landscape together with an invisible fabric of light and data, making a vast, empty world feel intimately connected. The invisible threat of radiation demands a solution measured in meters of solid mass. This is the domain of the radiation shield Regolith mover, a machine of monumental simplicity and purpose. Think of it as a patient, robotic giant, a titan of bulk movement whose intelligence lies in its single-minded dedication to a fundamental task: piling dirt. These are not fast or agile machines, but slow, powerful behemoths built for endurance, their wide tracks or massive wheels designed to distribute their immense weight over the fragile alien soil. Their tool is often a vast, blunt blade or a deep scoop, and their mission is written in the landscape itself. Guided by the colony's central blueprint, they begin their quiet, relentless work. One might spend weeks methodically pushing loose regolith into a towering, crescent-shaped berm around a cluster of habitats. Another might slowly, deliberately crawl over the curved roof of a printed structure, depositing and compacting layer upon layer of rocky soil until the building is buried under a thick, protective blanket. This is passive shielding at its most elemental. While active magnetic fields or complex water walls are possible, there is no substitute for sheer mass when stopping high-energy cosmic rays and solar particles. Several meters of local soil provide a barrier as effective as concrete, absorbing and scattering the dangerous radiation before it can reach the fragile biological systems inside. The mover's work transforms architecture, turning standalone buildings into what appear from the outside to be simple, grassless hills or bunkered mounds, their human-designed shapes erased beneath a natural-looking armor. This machine operates with a profound autonomy of scale, calculating the precise volume of material needed, navigating to the stockpiles created by the excavators, and executing its earth-moving plan without pause. It embodies a critical truth of off-world living, that ultimate safety often comes not from advanced technology, but from the intelligent, automated application of the oldest building material in the universe, the very ground beneath our feet. Buried treasure is useless if you cannot refine it into something you can breathe or burn. This is the purpose of the In-Situ resource utilization processor, a silent chemical plant that performs the ultimate alchemy, transforming alien dirt and thin air into the very elements of survival. Unlike the mobile excavator, this machine is often a stationary or semi-mobile factory unit, a complex labyrinth of pipes, reaction chambers, and storage tanks. Its singular, vital job is refinement, taking the raw harvest of the New World and turning it into pure, usable commodities. On the Moon, one processor might focus on a single, life-giving element, oxygen. It ingests the regolith sorted by earlier machines, rich in minerals like ilmenite. Inside a sealed reactor, it subjects this material to intense heat, often from concentrated sunlight, and a carefully introduced chemical agent like hydrogen. This process, called reduction, breaks the chemical bonds, liberating the oxygen atoms trapped within the rock. The machine then captures this gaseous oxygen, purifies it, and compresses it into tanks, creating a breathable atmosphere for habitats or a vital component of rocket propellant. On Mars, the challenge and the chemistry are different. The processor there is a master of the thin, carbon dioxide-rich air. Using a method like the Sabatier reaction, it combines Martian atmospheric carbon dioxide with hydrogen, which might be imported or extracted from water ice. With the help of a catalyst and heat, the reactor transforms these basic ingredients into methane fuel and water. The methane becomes the propellant for return vehicles or local transport, while the water is a bonus resource for the colony. This is the closed loop made real. The processor does not just find resources, it completes the cycle, ensuring that the colony's needs for air, water, and fuel can be met increasingly from local sources, inch by inch reducing its dependence on Earth. It is the quiet, humming heart of self-sufficiency, a machine that breathes for the colony before the first human lung takes a breath, teaching a dead world how to sustain the life that is coming. Even the most perfectly built structure is not a static monument, but a living system under constant, invisible stress. The silent watch that guards against this slow decay is the autonomous quality inspector, a fleet of small, vigilant drones that see what the human eye cannot. These are not construction drones but diagnostic specialists, each equipped with a suite of non-invasive sensors. They move in a constant, quiet patrol across the colony's growing skeleton, their mission to find failure before it ever becomes a crisis. Some hover before a habitat's curved wall, their high-resolution cameras scanning every square centimeter for the faintest hairline crack in the printed regolith. Others cling to the welded seams of a greenhouse frame, using ultrasonic probes that send sound waves into the metal, listening for the subtle echo that reveals a hidden flaw within the bond. A third group might fly along power cables or pipeline routes, their thermal imaging sensors painting a heat map of the infrastructure, instantly spotting a friction point or an electrical resistance issue that manifests as a dangerous hotspot. This is preventative medicine for architecture. The drones do not wait for a leak or a collapse. They actively seek the earliest possible signs of wear, the microscopic fractures caused by thermal cycling, the slight warping from subsurface settling, or the gradual fatigue in a load-bearing joint. Every anomaly they detect is not merely logged, it is instantly geo-tagged and uploaded into the colony's central digital twin, the living model of the entire outpost. This creates a dynamic health monitor for the settlement itself, a constantly updating diagram where potential problems glow with urgent priority. But the inspector's job does not end with diagnosis. Their report triggers the next step in the automated cycle, alerting the precise repair system needed for the issue. A micro crack in a printed wall might summon a smaller, mobile printer to patch the spot with an identical material blend. A defective weld flags the coordinates for a dedicated repair drone to grind and reseal the seam. This creates a closed loop of maintenance where detection and correction are two parts of a single autonomous process. The colony, therefore, is never finished. It is perpetually being tuned and healed by these silent guardians, ensuring that what was built to last actually does, through millions of day-night cycles without a single human needing to pick up a tool. A colony's greatest enemy is not the initial void, but the slow, inevitable decay that time imposes on everything it touches. This is where the self-repairing drone takes its quiet, essential place in the cycle, a machine whose purpose is not to build but to preserve. While the quality inspectors act as the diagnostic eyes, these drones are the healing hands, specialized for the constant, gentle surgery required to keep a settlement alive. They operate from a simple, profound principle that maintenance must be as autonomous as construction, or the entire endeavor will eventually crumble under the weight of its own upkeep. Imagine a small, mobile unit, perhaps a wheeled bot or a multi-rotor flyer, that receives a precise alert from the inspection network. Its mission is singular and clear: to mend. One variant might approach a hairline fracture detected in a printed regolith wall. From an onboard reservoir, it extrudes a paste made from the same local dust and binder used by the large Gantry printers, carefully filling the microscopic gap and smoothing it over, effectively making the wall forget it was ever damaged. Another drone tasked with infrastructure might patrol the paved roadways. Using a compact resurfacing tool, it identifies a section worn down by constant Rover traffic, lays down a fresh layer of processed regolith, and sinters it on the spot, leaving behind a seamless patch that restores the road to perfect condition. Perhaps most critically, a different model attends to the solar arrays. Upon detecting a cracked or underperforming photovoltaic cell, its delicate manipulators unclip the damaged unit, stow it for recycling, and slot in a fresh cell from a small onboard magazine, all without the array ever needing to shut down. These drones do not work from a blank slate. They work from a living blueprint of wear and tear, drawing their repair materials from centralized depots stocked by the resource processors, or, in a beautiful closed loop, from the very components they remove and recycle. Their existence transforms the colony from a static collection of buildings into a living, responsive organism, one capable of healing its own minor wounds. This continuous, silent caretaking is what turns a heroic first foothold into a permanent home, ensuring that the future we build among the stars is not a fleeting monument, but a legacy that can sustain itself, one microscopic repair at a time. The ultimate escape from a world's gravity may not begin with a roar, but with a silent, magnetic slide. As the colony's industrial base matures, a new ambition takes shape, constructing a celestial catapult that can launch cargo into orbit without a single drop of chemical fuel. This is the work of the Magnetic Launch Rail Assembler, a system dedicated to building a mass driver, a linear accelerator stretching for kilometers across the stark lunar or Martian plane. The machine itself is a marvel of coordinated precision, likely a convoy of specialized robotic units working in perfect sequence. The first unit is a foundation layer, a mobile gantry that prepares the ground with laser leveling, creating a perfectly flat and stable bed of sintered regolith. Following closely behind, a second machine, the rail placer, takes over. Its robotic arms handle long, slender segments of superconducting or highly conductive material, each one a critical section of the future track. With micrometer accuracy guided by orbital positioning satellites, It aligns and secures each segment end to end, ensuring the conductive path is flawless and continuous for its entire, staggering length. Parallel to this, another unit installs the powerful electromagnets or linear motor components at precise intervals along the track, burying their power and cooling conduits. The final structure resembles a long, slender scar on the landscape, a pair of silent rails pointing toward the black sky. The principle is elegant physics, not explosive chemistry. When operational, a sled carrying a cargo container is placed on these rails. As massive electrical currents pulse through the system in a carefully timed sequence, the sled is magnetically accelerated along the track, faster and faster, in near total silence. By the end of its several-kilometer-long journey, it reaches orbital velocity, releasing its payload in a graceful arc that carries it into space. This machine builds the gateway to a sustainable off-world economy. It means mined metals from the moon can be launched to orbital factories for a fraction of the fuel cost of a rocket. It means Martian water ice can be efficiently sent to fuel depots waiting at Lagrange points. The assembler does not just lay tracks, it builds the first true highway off the planet, turning the colony from a consumer of Earth's launches into an exporter of its own riches, using nothing but electricity and the silent, irresistible push of magnetic fields. But a magnetic catapult launches only cargo, not people. For true sanctuary from a world's harsh surface, we must look not up but down. A new kind of machine begins its work, a subterranean architect called the underground habitat borer. This is a titan of the depths, a cousin to the tunnel boring machines used on Earth, but reimagined for an alien environment where gravity is weak, the air is non-existent, and the rock itself is a different kind of challenge. Its scale is difficult to grasp, a cylindrical behemoth longer than a football field. Its face a rotating disc studded with cutting teeth made of super-hard materials. It does not dig a small service tunnel, it carves out a future metropolis. As it grinds forward with a deep, resonant hum felt through the ground, it excavates a vast, perfectly circular cavern, wide and tall enough to house entire city blocks. Its genius lies in its integrated construction. While the cutting head chews through bedrock, a trail of robotic arms immediately behind it springs into action. They spray the newly exposed rock walls with a quick-setting sealant, creating an instant, airtight liner that stabilizes the geology and locks out any trace of the thin outside atmosphere. Following that, these same arms begin assembling a secondary, reinforced arch structure against the sealed wall, a skeletal framework of interlocking segments that will bear the long-term structural load. The borer is not just making a hole, it is building a finished, pre-shielded room as it goes. The result is a cathedral-like space, born ready for human occupation. These underground caverns offer the ultimate protection, buried under hundreds of meters of rock that serve as a perfect radiation shield and a superb insulator against the wild temperature swings above. They provide a stable, secure volume for expansive habitats, vast agricultural domes, or shielded storage for volatile resources. Each rotation of its cutting head is an act of profound creation, turning the most hostile element of a new world, its very crust, into the safest possible home. This machine redefines the frontier, proving that on other worlds the most advanced architecture may be the simplest, a return to the cave, engineered not by nature, but by a silent, patient machine carving out a future in the eternal dark. Every arrival and departure begins with a safe place to stand. The Precision Landing Pad Fabricator is that guarantee, a robotic ground crew that transforms chaotic, unpredictable terrain into a flawless, engineered runway for visiting spacecraft. This machine operates on a principle of absolute certainty, knowing that a single loose rock or an uneven surface could spell disaster during the violent, dusty chaos of a rocket landing. Its work is a meticulous, multi-stage ritual of preparation. First, its array of forward-facing sensors and sweeping arms scans the designated zone, identifying every boulder larger than a fist and every dip or rise that exceeds a tolerance of mere centimeters. Then, with gentle but firm purpose, it begins to clear and sculpt. Small, articulated grapples lift and relocate stones to a perimeter berm, which itself will act as a blast wall. Simultaneously, adjustable grading blades on its undercarriage skim across the ground, filling depressions and cutting down high spots until the area is geometrically perfect, a vast, flat circle etched into the landscape. But creating a level dirt field is only the first step. The true transformation comes next. The fabricator moves to the perimeter of the now perfectly graded disc and begins a slow, spiraling inward path. From a trailing assembly, it deploys a powerful, focused energy source, often an array of microwave emitters or concentrated solar mirrors. This energy is directed at the freshly leveled regolith, heating the dust and soil particles just below their melting point. The process, called sintering, fuses the loose grains together into a continuous ceramic-like sheet. Layer by layer, as the machine spirals inward, it creates a monolithic, pale gray platform that is rock-solid, dust-free, and highly resistant to heat. This sintered surface is critical, as it prevents the rocket's exhaust plume from scouring out a dangerous crater and hurling supersonic debris at the landed vehicle or nearby infrastructure. The final pad is more than a parking spot. It is a calibrated instrument. Embedded sensors within the sintered material can provide real-time data on weight distribution and structural integrity to a landing spacecraft, and subtle, reflective markings around its edge guide final descent algorithms. This machine performs the last, vital act of preparation before the first human ever sets foot on this new world, ensuring that when the ship of explorers finally touches down, it does so on a foundation of unshakable robotic certainty. Beneath the sintered landing pads and the quiet hum of the processor plants, another kind of lifeblood must flow. The autonomous cable-laying rover is a patient, methodical machine, a subterranean scribe etching the colony's nervous system just below the surface. It resembles a large, low-slung vehicle with a singular, linear purpose. At its front, a narrow, precision plow blade slices into the regolith, opening a neat, shallow trench only a few centimeters deep. As it moves forward at a steady, unhurried pace, a spool mounted on its back unwinds a continuous line of specialized cable, guiding it directly into the freshly cut groove. This is not ordinary wiring, it is armored cable, sheathed in multiple layers of protection against radiation, temperature extremes, and the abrasive grit of the soil. One line might carry high-voltage direct current from the distant solar fields. Another might contain bundles of fiber optics for near-instantaneous data. Immediately behind the laying mechanism, a second tool engages, a gentle, sweeping blade that pushes the excavated soil back over the buried line, sealing it away from the harsh surface environment. In one smooth, continuous operation, the machine performs the entire cycle: dig, lay, and cover, leaving behind only a faint, healed scar on the ground. This relentless, linear progress is what weaves a distributed grid into being. The rover works from the central network map, connecting the dots between power sources and habitats, between communication towers and sensor arrays. It does not lay a single, fragile line, but a redundant, looping web. If one cable segment is later damaged by a shifting rock or some unforeseen event, the network can automatically reroute power or data through an alternate path, ensuring that a single point of failure cannot plunge a sector into darkness or silence. This machine embodies the principle of resilience through distribution. Its work is invisible once completed, buried and forgotten, which is the ultimate measure of its success. It creates the hidden, constant flow that allows every light to switch on, every sensor to report, and every data packet from Earth to find its destination. proving that the colony's true strength lies not in its most visible monuments, but in these silent, buried veins of energy and information. A silent, grey film steadily settles over everything, an insidious threat more persistent than radiation or vacuum. This is the challenge of planetary dust, a fine, abrasive powder that clings with electrostatic tenacity, threatening to grind moving parts to a halt, blot out the sun from solar panels, and obscure the electronic eyes of every camera. To counter this, a specialized class of machines awakens, the dust mitigation units, the colony's dedicated custodians in a never-ending battle against entropy. These are not general-purpose cleaners, but precision tools designed for specific, critical surfaces. One variant might patrol the vast solar arrays on soft, rolling treads. At the end of a gentle arm, it deploys a brush made of specialized fibers that carry a mild electrostatic charge, opposite to that of the dust. As it sweeps across the panels, it does not scrub, but instead repels the particles, lifting them away on a cushion of opposing force and letting the weak alien breeze carry them off. For the sensitive lenses of navigation cameras or scientific instruments, a different approach is needed. Here, a smaller, more delicate unit might use a brief, precisely directed puff of inert gas, a miniature wind that blows the dust away without any physical contact that could scratch the fragile optics. Perhaps the most ingenious systems are the proactive ones. A mobile applicator rover might travel along the outside of habitat airlocks or the joints of robotic arms, spraying a transparent, ultra-slick nanomaterial coating. This coating creates a surface so smooth that dust particles cannot find purchase, simply sliding off with the barest vibration or tilt. This constant, quiet work is not about cleanliness for its own sake, it is about preservation. A dust-choked solar panel can lose half its power output in a matter of weeks. A single grain jammed in a wrist joint could cripple a vital assembly drone. The mitigation units operate on scheduled patrols, triggered by performance dips detected by the network or simply by the passage of time, a robotic reminder that on other worlds, survival is a daily act of maintenance. They are the unsung guardians of efficiency, ensuring that every watt of power is captured, every camera sees clearly, and every moving part continues to move, fighting back the creeping tide of dust one silent, methodical pass at a time. Even the most efficient colony will produce what it cannot immediately use, the inevitable byproducts of life and industry. Here, the waste processing and recycling bot transforms what would be a dangerous burden into a profound resource, closing the circle of survival with elegant, autonomous efficiency. This system is less a single machine and more a distributed network of specialized units, a silent sanitation crew working in the colony's hidden metabolic pathways. Their work begins with collection, as small, discrete autonomous units gather both solid and liquid waste from habitat modules, laboratories, and workshops, transporting it through sealed conduits to a central processing facility. Inside this sterile, sealed plant, the true alchemy begins. The first stage is automated sorting, where robotic arms equipped with advanced sensors and gentle grippers perform a rapid, precise triage. They separate plastics and composite materials from organic matter, isolate metals from glass, and divert any hazardous chemical byproducts into secure containment. Nothing is treated as mere trash, everything is seen as potential feedstock. The organic waste, including what comes from human habitation and greenhouse trimmings, is then subjected to a controlled breakdown process. In large, anaerobic digesters, microorganisms, carefully cultivated and maintained by the system, consume this material. Their digestion produces two valuable outputs: methane gas, which can be purified and used as fuel or a chemical feedstock, and a nutrient-rich slurry that can be returned to the hydroponic systems as fertilizer, completing the food cycle. Meanwhile, the sorted plastics and other complex polymers are fed into thermal processing units. Through a method called pyrolysis, they are heated in an oxygen-free environment, breaking them down not into toxic ash, but into reusable hydrocarbon gases and a carbon char that can become a strengthening additive for three-dimensional printer resins. Even the water reclamation process is a masterpiece of recycling. Wastewater from all sources undergoes a multi-stage purification journey, passing through filters, reverse osmosis membranes, and advanced oxidation processes that remove every trace of biological and chemical contaminant. The result is water so pure it meets the standards for both drinking and the sensitive chemistry of life support systems or industrial processes. This machine network embodies the ultimate principle of a sustainable off-world presence, that there is no away. Every output of the colony becomes an input for another process. The air you exhale contributes carbon dioxide for the greenhouses. The packaging from a shipped component becomes raw material for printing a new tool. The water you use is endlessly cleaned and returned to you. It is a quiet, constant demonstration that survival on a world with no natural biosphere means building one, a closed loop where every element is precious and nothing is ever truly wasted. The silent architecture of the future is not confined to planetary surfaces, but extends into the gentle currents of orbital space, where a different kind of construction defines a new way to live. Here, the mission shifts from battling gravity to harnessing its most subtle effects, creating environments where humans can thrive not just for months, but for generations. This is the work of the Gravitational Anchor Deployment Craft, an autonomous spacecraft whose purpose is to spin the void into a semblance of home. Envision a specialized vessel, sleek and equipped not with engines for long journeys, but with precision thrusters and powerful, robotic winching systems. Its cargo is a spool of material that seems almost impossibly slender for its task, a tether woven from carbon nanotubes or advanced polymers, stronger than steel yet lightweight enough to be deployed across vast distances. The craft's mission begins at a fledgling orbital station, a collection of modules docked together in the weightless quiet. With meticulous care, it detaches one key habitat module, using its thrusters to gently ease it away from the central cluster, playing out the incredible tether between them like a cosmic fishing line. Once the two masses are separated by perhaps a kilometer or more, the craft's most critical phase begins. It initiates a slow, controlled burn, setting the entire system, the two modules and the tether connecting them, into a steady, graceful rotation around their shared center of mass. This spin creates a force that is, for all practical purposes, artificial gravity. Inside the modules, especially those farthest from the center of rotation, this force pushes objects and people toward the outer hull, simulating the steady pull of a planetary surface. The deployment craft does not just connect two pieces, it architects an experience. It carefully adjusts the spin rate, calibrating the centrifugal force to match Martian or lunar gravity for research, or even Earth normal for long-term health. Its sensors constantly monitor tension on the tether, making micro-adjustments to the station's attitude to counter the subtle drag of the tenuous upper atmosphere or the gravitational tugs from nearby celestial bodies. This machine constructs the fundamental framework for permanent orbital life, transforming a fragile cluster of tin cans into a resilient, rotating ecosystem. It builds the condition necessary for bone density to be maintained, for fluids to behave normally, for gardens to grow with roots pointing in a consistent direction. This is how we learn to carry a piece of home with us into the deep sky, not by recreating a planet, but by mastering the physics of spin, crafting gravity itself as just another piece of infrastructure in the silent shipyard of orbit. This final, intricate web of infrastructure, both on the ground and in orbit, requires a masterful system of coordination. High above the rust-colored plains or the charcoal-gray highlands, a different kind of architect begins its work. The Autonomous Satellite Constellation Deployer is a mothership of silent potential, a spacecraft whose sole purpose is to seed the sky with a brain. It arrives after a long coast through interplanetary space, its cargo bay filled not with a single large satellite, but with dozens, sometimes hundreds, of small, identical units, each no larger than a briefcase. These are not traditional, complex satellites with bulky instruments. They are streamlined nodes of a distributed intelligence, each carrying a radio transceiver, a simple processor, and a compact solar panel. The mothership's mission is one of precise, patient distribution. It does not simply open a bay door and eject its cargo into a chaotic cloud. Instead, it uses its own propulsion system to enter a carefully calculated orbit around the moon or planet. Then, with the calm precision of a cosmic clockmaker, it begins a slow, systematic dance. At a precisely timed moment, a small, spring-loaded mechanism gently pushes a single satellite out into the void, giving it a slight nudge. The mothership then fires its thrusters for a few seconds, shifting its own orbit by a tiny fraction. It waits, orbits, and then repeats the process, releasing the next node at the exact right position to fill a specific slot in the grand design. This meticulous, automated choreography continues for weeks or months until the entire fleet has been dispersed. Once free, each small satellite powers on, its solar panels unfolding like metallic petals. They begin to talk to one another, a quiet chatter of radio signals across the void. Using onboard navigation and the mothership's initial deployment data, they autonomously adjust their positions with tiny, fuel-efficient thrusters, spreading out to form a perfect geometric mesh. This is not a random scatter, it is the formation of a complete, self-configuring network. From the surface, this constellation becomes an omnipresent utility. For a robotic rover navigating a deep canyon, it means constant line of sight with at least 3 satellites, providing instant, centimeter-accurate GPS positioning on an alien world. For the colony's communication network, it means a resilient, redundant web where data packets can hop from node to node, ensuring that a video call from a remote research outpost never drops, even if one satellite fails or passes behind a mountain. The mothership, its primary mission complete, might then assume a new role as a central relay hub or simply go silent, a spent shell that drifts as a monument to its own success. This machine builds the final, unifying layer of awareness, creating a shared nervous system in the sky that watches over every machine, guides every traveler, and connects every distant voice into a single, coherent conversation across a new world. All of this frantic, distributed activity begs a final question: who is in charge? The answer is not a who, but a what, the silent conductor of this mechanical orchestra, the AI Foreman and network hub. This is not a physical machine that moves dirt or welds metal, but the central nervous system of the entire endeavor, a stationary supercomputer or a distributed artificial intelligence network that lives within the colony's very infrastructure. Its primary input is a flood of data, a constant, real-time stream from every single machine we have described. It receives the structural integrity report from a quality inspector drone, the remaining battery level from a solar panel cleaning unit, the precise location of a resource stockpile from an excavator, and the weather prediction for an approaching dust storm from the Orbital satellite constellation. Its genius lies in synthesis, in seeing the entire, sprawling project not as 25 separate tasks, but as a single, interdependent organism. With this God's eye view, the AI Foreman performs a relentless, silent calculus of optimization. It dynamically reallocates resources, perhaps diverting a transport rover from a low-priority task to deliver emergency binder to a 3-dimensional printer whose local supply is running low. It solves fiendishly complex logistical puzzles in real time, recalculating the entire construction schedule because a habitat borer has encountered an unexpected layer of exceptionally hard rock, delaying its progress by 12 hours. The system understands that this delay will push back the installation of life support in that module, which in turn affects the arrival schedule for the human crew. So it automatically adjusts, perhaps reassigning welding drones from a nearly completed greenhouse to accelerate work on a different habitat cluster, ensuring the overall timeline remains intact. It is the ultimate project manager, one that never sleeps, never overlooks a detail, and operates on a scale of complexity no human team could ever hope to match. This central intelligence is what transforms a collection of talented machines into a single, unified builder. It is the quiet mind behind the muscle, the reason a colony can rise from dust with such breathtaking efficiency and harmony, proving that the future of construction lies not just in stronger arms, but in a wiser, all-seeing eye. This silent orchestra of 25 machines finds its harmony not in isolation, but in a profound, interconnected dance. Each unit is a specialist, yet its true purpose is only unlocked when its work becomes the foundation for the next. This is a symphony of steel and silicon, where the entire system is far greater than the sum of its autonomous parts. The secret to their coordination lies in a principle borrowed from nature itself, called Stigmergy. It is a form of indirect communication where an agent's action modifies the environment, and that modification guides the next agent's behavior. Think of a colony of ants where one leaves a pheromone trail, and the next ant reinforces it, creating a highway without a single instruction being spoken. Our robotic builders operate on a vastly more sophisticated, yet spiritually similar level. The autonomous site surveyor does not tell the excavator where to dig. Instead, it creates a hyper-detailed digital twin of the landscape. This model is the shared environment, the common ground of data that every machine can see and understand. When the excavator and sorter then choose into that mapped terrain, it is not just moving dirt, it is actively transforming the physical world into a new state of organization. It sorts the regolith, piling usable aggregate here and valuable mineral concentrate there. These sorted piles are not random, they are a physical message. The mobile three-dimensional printing Gantry arrives, scans these newly created resource stockpiles with its own sensors, and recognizes them as its raw material. The excavator never sent a signal saying, "The bricks are ready." It simply made the bricks available in the world, and the printer, reading the environment, knew exactly what to do. This creates a beautiful, self-reinforcing cycle of production. The printer uses the sorted aggregate to build a structure, perhaps a foundation for the in-situ resource utilization processor. Once built, that processor begins converting local materials into breathable oxygen. That oxygen then supports the human technicians who might later maintain the very network hub coordinating the machines, closing a loop of creation and sustenance. Every output is an input, every change in the landscape is a command for the next stage. The communication towers and satellite constellation provide the constant data stream that makes this environmental language instantaneous and precise, while the AI Foreman acts as the composer, ensuring the tempo of this Stigmergic symphony doesn't falter. This is how you build a world, not with a single blueprint, but with a living, responsive conversation between mind, machine, and the very soil they are transforming. The silent symphony of machines we have witnessed is more than a list of tools. It is a single, transformative vision made real. It is the blueprint for turning silent, barren worlds into vibrant, living extensions of our own civilization, not through heroic, individual effort, but through the quiet, collective industry of autonomous systems we designed and sent ahead. This is the profound takeaway. Our future in space will be physically built not by astronauts in suits with wrenches, but by the robotic proxies of our imagination and ingenuity. We are learning to build with the materials at hand, to close every loop of resource and energy, and to create environments that can sustain themselves long before the first human footstep marks the soil. This is not about replacing humanity's role in exploration, but about fundamentally redefining it, shifting our purpose from construction crew to architects and overseers of a new kind of Genesis. And the ripple effects of this vision already touch our home planet. The same principles of autonomous construction, in-situ resource utilization, and closed-loop recycling are informing radical solutions here on Earth, from robots that rebuild eroding coastlines with local sand to AI-managed systems that turn urban waste into new building materials, tackling our own environmental and logistical challenges with off-world ingenuity. The future of building is being written in the dust of other worlds, and it is a story of silent, intelligent creation. If you want to continue exploring the technologies that will shape our tomorrow, from robotic architects to orbital factories, make sure you subscribe. The next chapter of our future is being designed right now, and the conversation is just beginning.